Hello, so thank you for having us at CINCON 2025. So it's our pleasure to present our work over here. So before our talk, we already have a lot of really brilliant talks, and it's all focused on how attackers work, how APT infiltrate the satellite systems, and all the different attack techniques. But in our work, you have to shift your viewpoint from the attacker side to the blue team side. So we are mainly focused on how we utilize the language model to construct a command line graph that can help the cybersecurity analyst to capture the unhidden command line during the cybersecurity instance. So whenever I talk this topic to share this topic to others, the first question I would have is that why would I need a language model that help me to construct a graph? Why can't I just use for example, like the space, just cut the command line into segment with the spaces, and it can still works? And our answer to that is that it works for a certain level. But if you want to have more contextual awareness regarding to each malicious command lines, you need to have a graph, because we can use different relationship between different command line segments that can help us to infer the uncovered malicious command line. And in our real world cases, it helps us to identify multiple APT groups command lines in the real attack. So before we started, I would like to introduce today's speaker. So the first is Laura Zheng. So she is the data science intern at CyCraft data science team, and she is now the third-year computer science student at CyCraft at National Taiwan University. And her research topic would involve like the cybersecurity and also for the scale of the educations. And for the second speaker, it would be Jerry Lin. So his main research focus is on how to utilize different language model and also the Bayesian-based models to predict malicious activities in the cybersecurity instance. And also, he's also really good at using different graph type algorithm to identify vulnerabilities in AD environment. So that's Zhe Yu. And finally, it's me. So my name is Cheng-Lin, and I'm the director of the data science at the CyCraft. So I'm basically the annoying boss of these two speakers. So if you guys love today's presentation, all the credits goes to Jerry and Laura. And if you don't like it, it's all on me, okay? So before we start, first, I would like to say thank you to CINCON, because I saw the organizer is over here. So last year, we were here as well. So we present a bully rack. So it's a comprehensive evaluation framework that can test the RAG systems. And after this talk, we talked to a lot of people and a lot of attendees, and they give us some brilliant ideas that can improve our work. So we extend our work, and then we submit it to the Cold Blue Japan, and also got accepted. So this year we also want to, after this call, we can talk to some of the audience, and hopefully we can get some really good advices from you guys, so we can keep improving our works. So before we started, I would like to start with a very simple quiz, because in my talk I don't like to just be me and then speak to yourself, but also have some interaction with you. So let's start with a very, very simple question. So here's a command line over on the screen, you can see it. So can you tell me how many commands in this command line? So it's either be 2 commands, 3 commands, or more than 4. So if you think it's 2, please raise your hand. Okay. If you think there are 3, please raise your hand. Okay, I see some hands. Okay, great. How about 4, more than 4? Okay, cool. So that's great. So nobody choose 2, which is good, because you guys are cybersecurity professionals. And if I see any person raising on the second one, I will be very terrified. Okay, so let's dive into these cases. So in these cases, we can First, separate this command with this one. So this is the first command. And also, we can use this simple technique like we just use the spaces to cut it into this command. And also, there's a sub-command is between that can be utilized by these both commands. So it actually has the 3 command lines in this command line. However, if we look deeper, or you can ask deeper, what are the other components among this very complex command line? As you can see, we can actually separate it into more segments. So there's an AND operation that can be easily be missed by a lot of techniques. And also, let me use the laser point over here. So as you can see over here, you can see, although there's a command line, it's called a dirce users directory, it's also the part of the argument of a subcommand. So this shows a nature of the how it's very difficult to really understand the real attention of the command line, because it depends on where this command line to be positioned. So if it's positioned as an argument, then the whole meaning of the actual command line will be changed a lot. This is why we say there are some limitations of the very simple technique that, for example, using the spaces to just segment your command line. That's why we need a language model that can have the contextual awareness that can help us to identify the true meaning of the segment. So in the real world cases, it's the real world cases. As you can see on the screen, there are 3 different command lines which is actually used in one of our customers. So among these 3 command lines, there are some part of this command line will be linked together. So for the first, as you can see on the last one over here, you can see ifconfig. So if you are using a traditional approaches, you can see a lot of people will not identify ifconfig as a malicious command because it can be used by both IT administrations and also the hackers itself, right? So this is what we call it as a gray command. So it all depends on how this command is positioned on the context that you are in. So so that's why we need to to try to convert this command line into graph. So if we convert these 3 command line into graph, we can merge them together into this really huge command line. It's actually an instant, so it's a list of command that we can merge it into. So once we have this really large command line graph, we can then use a lot of great attribute of the graph. So that can help us to infer that which command which is not be identified at the first place, but we can utilize it further. So this is it's the basic idea of our research, and then follow on the Laura and Jerry will give you a much deep dive into our research. So I will hand it over to Laura.
So thank you, George. And now I'll do the introduction of our work, CLINKER. And let's start by defining what we mean by forensics in cybersecurity. In our context, an event refers to a command line execution record along with its associated metadata such as process ID, username, and timestamp. And the primary goal of forensics is to identify malicious events within a large set of system activity logs. Some malicious events are context-free, meaning that they can be identified on their own, like the direct execution of a malicious file. While others might be contextual, they might have to depend on other contexts, where a seemingly benign command turns malicious because it occurs within a suspicious context, such as being triggered in a malicious process chain. And I'll walk you through an example to further illustrate why context matters in cybersecurity forensics. Sometimes the semantics or behavior of a command alone aren't enough to determine whether it's legitimate. Take this command, who am I, for example. On its own, it looks completely benign. What harm can it do? But when it's used in a script, executed silently and ran from a suspicious directory, it might indicate an attacker gathering system information as a part of a larger malicious sequence. As for the second example, it might be doing silent data collection during the staging phase of an attack. However, it might also be completely benign. So these examples make it clear that we need context to make informed, accurate forensics judgments. Okay, and LLMs are getting more powerful than ever. And when it comes to detecting context-aware malicious events, most previous work focused on using LLMs after clustering. They use LLMs to explain a cluster of events. However, how those events are clustered in the first place really matters for everything that comes after. And yet, this crucial clustering step usually happens without leveraging the power of LLMs at all. So how can we bring LLMs into the early stages of the detection pipeline? First, we have to recognize a key limitation. That is, LLMs have a limited context window. They simply can't take in all events at once. For example, you can see that command listed on the PowerPoint. This single command already has 46 tokens in Llama 3. So if we had 10,000 events, that's around 500,000 tokens, way beyond what any LLM can take in. And analyzing events one at a time doesn't work either. That would just take us back to context-free judgment, which, as we've seen, will not work. So the question is, how can we leverage the power of LLMs to identify related contexts of events for judgment? This brings us to an RAG-inspired approach. Retrieval-augmented generation, or RAG, is a method where an LLM first retrieves relevant external information before generating a response, allowing it to reason with more context than its prompt alone provides. Similarly, in forensic analysis, we propose RAF, which is retrieval-augmented forensics. And in RAF, what we do is we retrieve related events first, then we judge whether the target events are malicious. But there's a difference between RAG and RAF. In traditional RAG, the goal is to retrieve all content relevant to a query without redundancy. In forensic analysis, however, it's more nuanced. We need to perform multi-aspect retrieval, context-aware retrieval, and we have to do iterative retrieval judgment. And I'll dive into these notions later. So what exactly is multi-aspect retrieval? Well, events can be related to each other in many different ways. They might belong to the same process tree, or they might reference the same file, or they might point to the same IP address, or they might just have similar command patterns. Now you might think, why not just use command line embeddings and connect events with high cosine similarity together? But here's the case. You can see this grid on the right-hand side. This grid is the pairwise text embedding similarity of the commands on the left-hand side. And take a look at the command pairs on the upper left corner of the grid. They have high embedding similarity. But if we simply set a similarity threshold, say 0.5, to decide whether two commands should be linked, we end up missing many meaningful relationships. For example, take a look at these two commands. They share the same IP point, and they should be linked together in some way, but they wouldn't in this scenario because the similarity score of their embeddings is only 0.2. So clearly, relying on embeddings alone is not sufficient. We need to consider multi-aspect relationships. Regarding context-aware retrieval, it is important to note that different contexts can change the classification of an event from malicious to benign. let's take a look at the unclassified command in the red box. At first glance, it might seem suspicious, and it is related to both a benign and a malicious command through different aspects. However, since it is linked to the benign command through that green path, it is more likely to be benign. In reality, this command is most likely generated by IT automation tools. And finally, there is the iterative retrieval judgment process. Take this example. We start with a known command that has already been flagged as a malicious event, and that would be our initial point. The second command, which is the part of the same malicious activity, can be discovered in a single pass through the same path relationship, which is highlighted in red. And that's straightforward. However, the third command, although still part of the broader malicious chain, isn't directly linked to the initial event. It is not picked in the first pass. And that's where iterative retrieval becomes crucial. By repeatedly expanding the context, link by link, we can uncover additional related events that wouldn't be captured otherwise in a single run. This multi-step retrieval process ensures that we don't miss important parts of the activity chain and enables more complete threat reconstruction. So let's recap quickly what I mentioned in the previous slides. Well, RAG retrieves query-related blocks to aid the generation process. RAF starts with some malicious event seeds, then iteratively searches and retrieves correlated events via multi-aspect and context-aware retrieval. In each run, a judgment is made by an agent, and newly determined malicious events are added back to the event seed list. And to perform retrieval augmented forensics effectively, it is crucial to have a data structure that encodes multi-aspect relationships and clustered related events together, and also supports iterative retrieval judgment process. And that brings us to our work, CLINKER, which creates command line graph representations designed as an augmentation to the original event graph to link together events with related command lines through multiple aspects. Okay, now let me give you an overview of what CLINKER does. It takes command lines as inputs and outputs graph representations for each command. The graphs are then merged together to form the final event graph. As for the process pipeline of a single command, the input commands are processed in parallel by two LLM-based components, a command extractor that identifies standalone commands, and a command parser that extracts token tag pairs from the command. And the output of these two components are then fed into a graph construction algorithm, which builds the final graph. To help us understand relationships between commands more clearly, we start by defining how command lines are structured. A single command line actually includes several smaller standalone command lines. We can identify and extract them by looking for a few common patterns listed on the chart. And these patterns include encapsulated, where a command runs another within its scope, and command substitution is where a command is executed in a subshell. We also have pipelined commands, where commands are connected via pipes, and chained commands, where commands are connected using logical operators. And it is notable that standalone commands aren't necessarily executable by some shells alone. And next, we also define several key tokens that appear within a command line to help us analyze its semantic structure. These token tag pairs include command, CMD, which is the main tool or executable invoked in a command line, like echo in the example. We also have subcommands, sub, which are context modifiers that specifies the behavior of a CMD, like log in git log. And next, we have option, opt, which are flags or switches that modifies how the CMD or sub behaves. And they are often with a slash or a minus sign. Next, we have arguments, arg, which are literal values or parameters passed to a command line, subcommand, or an option. And last but not least, we have operators, OPR, which are shell-level symbol controlling flow, redirection, or piping between commands, like the greater than sign for redirecting output. The different tags of each token define different types of graph links, which can be helpful in forensics. Now, let me introduce our graph construction algorithm. We use a two-phase approach, and I'll walk you through how we build the graph for a single command. In the first phase, we start with the extracted standalone commands. For each one, we connect them back to the root command component. And the key idea here is to start from the longest to the shortest standalone commands, attaching each one to nodes on the deepest layer that contains it. So for example, we initially have this root command. And next, we try to connect the longest standalone command back to the root command. And for the next standalone command, it is not contained in node number 1, so it has to go back to the root command. As for the third standalone command, we can see that it is contained in both node number 1 and number 2. So we connect, we draw out links from both nodes to node number 3. And that completes our stage 1. In the second phase, we take the parsed token tag pairs and apply a similar idea. That is, we start from each leaf command node, and for each token, we find the deepest layer in the structure that contains it and attach it there. So for example, let's take a look at the double AND operator. It should belong in the root command since it appears nowhere else. So we attach it onto the root command. And another example is for this argument. As we can see, this argument is contained in the second to the deepest layer and by both nodes. So we draw links from those nodes to this argument. And after we apply the similar idea to all these token tag pairs, we get the final command line graph. OK, so we now know how to create graphs given token tag pairs and standalone commands. And the remaining question is, how do we build effective command extractors and parsers that can handle large volumes of command lines effectively? The idea is to design prompts and let the state-of-the-art large language models generate high-quality parsing results first. Then we can take those results to fine-tune a smaller model that can imitate the behavior of the LLMs, allowing us to scale efficiently with lower computational cost. And to understand how different parts of our training data contribute to the fine-tuning process, we ran an ablation study. On the input side, we include 3 components. First, we have the raw command line itself, which is the input command. Second, we have instructions that tells the LLMs what to do. And third, we have a prompt to tell the model to provide intermediate steps or a chain of thought that helps guide the model during inference, and we call that COT prompting. On the output side, we also include 3 components, which are the target output, which is the expected parsing or extraction result, a logic explanation, which describes what the command is doing, and again, the corresponding part of the CLT prompting, which explains why the extraction or parsing was done. OK, so the first setup SFT1, keeps only the system prompt on the input side. And the second setup additionally requires the model to generate the output logic of the command. And the third setup removes the system prompt while still requiring the generation of the output logic. So there are SFT1 to SFT3. For the fourth setup, it is a little bit special. It includes all components of the training data, and it can be actually seen as a form of knowledge distillation. That's because the model isn't just learning the correct outputs. It's also learning the reasoning behind the outputs. In other words, it's not only mimicking what the large model does, but also understanding why it makes those decisions. We wanted to investigate whether this added layer of explanation helps the smaller model generalize better and make more informed predictions. And now let's talk about how we evaluate our models. The goal here is to measure how similar the results generated by our fine-tuned models are to those from the LLMs. The models we chose for LLMs and small LLMs are listed here. And to measure similarity, we mainly use Jaccard similarity, which is the ratio of overlap between the predicted and target sets of extracted commands or token tag pairs. So the more the overlap, the higher the score. And if you're not familiar with what a Jaccard similarity is, there's a small illustration on the right corner. When the union of the area is 1 unit, the Jaccard similarity would be the intersection, the area of the intersection. And besides Jaccard similarity, we also have format parsability, meaning whether the model's output can actually be parsed, either as a proper list or a valid JSON. This tells us if the output is even parsable. Finally, we define a composite score that averages these two metrics, Jaccard similarity and format parsability. For Jaccard similarity, we only include entries where the outputs are successfully parsed, since you can't compare the structure if you can't parse them in the first place. Okay, now let's jump into the results. First, looking at the testing outcomes from different training setups, we can see that SFT2, which includes both the system prompt, the instructions, and the output logic, delivers the best performance out of the first 3 settings. We also observe that removing the system prompt leads to a larger drop in performance compared to removing the output logic. Based on this, we can infer that the importance of these data components may follow this inequality. That is, system prompt greater than output logic, while both components contribute positively to the performance. Also, we can see that the COT prompting design might be quite a good design, as it has the best performance out of all settings. So we use this setting for all experiments following. As for efficiency, the fine-tuned small language model runs about 20 times faster at peak than the original LLM. So our goal of making CLINKER both efficient and usable is indeed met by our approach. And now, let's dive a little bit deeper into the details and compare how different choices affect performance. First, let's start with the choices of large language models. We compare the performance of small LLMs distilled from command parser data generated from Llama 3 70 billion and QN 2.5 72 billion. The in-distribution data, which corresponds to the chart on the left-hand side, are synthetic data used for training and evaluation and are generated by multiple LLMs, while the out-distribution data is for testing, which is a subset of a really large dataset released by DARPA. We can see that Llama-generated data has better in-distribution results, but seems to fail to generalize, since you can see a significant performance drop from the in-distribution to the out-distribution results. Let's take a closer look at the differences between the data generated by Llama and QN. First, we'll examine the reasoning sections generated by both models for the same input command line. As we can observe, Llama tends to correct potential typos in the green box, which is especially helpful since the input command lines are synthesized and could contain errors. On the other hand, QN mistakenly classifies the call token as an operator when it should be classified as a subcommand instead. Overall, Llama outperforms QN in this case, providing more accurate and reliable reasonings for input command lines. Then you might think, but why is Llama having overfitting issues despite better reasoning? One possible reason might be that more format errors are generated with Llama for parsing data compared to QN. For example, Llama might make copying errors when copying Unicode characters from the input command line to the output result. And another interesting fact is, as we mentioned earlier, Llama tends to fix the input command line when it detects possible typos. But this may result in a case that the parse tokens don't appear in the original input command line, like in the case on the bottom. Thus, typos in synthesized data might have a more profound impact on the fine-tuning process, leading to overfitting. However, what's quite interesting to us, and also unexplainable by us currently, is that after we tried taking the mixed training method, that is, we train the command parser data and command extractor data together, the generalization issue seems to be resolved. As we can see, the indist and outdist results of Llama is now more consistent. Next, we also compared the performance of different small language models. We compared the performance of 4 models, which are QN 2.5, 0.5 billion, QN 2.5, 1.5 billion, DeepSeek R1, 1.5 billion distilled from QN, and also Llama 3.2, 1 billion. When using the mixed training method, we found that there are no significant difference between these models. So now, I'll hand over to Jerry, and he'll explain a real-world case study to us.
Hi, hello. So I'll now show you the result of applying CLINKER with different language model to the real-world case. So first, let's look into the actual events we considered. First, this event listed in the red box are malicious events, which we've seen before, and they actually share similar command patterns, like containing the echo bracket X, bracket E. And the second group of events, which are also malicious, but they do not share similar command pattern as those in the red box. But inside their command, there's some token that can be used to indicate their relationship to malicious events. And the third group are benign events, which are listed in the purple box. They share similar command patterns of their own. And some of the events on top of the 2 lists are actually linked to benign software, the net backup. So next, we show the graph constructed using these events. Here's the graph, and we didn't consider, for simplicity, we didn't consider the like parent-child process relationship in constructing a graph, and only consider the command line patterns. And although due to the randomness in computing the coordination, the 2 graphs may not look alike, but there are some properties that one can use to map one graph into another. Like for red dots representing the malicious events, they have much stronger link that pull them closer to each other, and so are the purple nodes. And one distinct point from the distilled model is this event, which is disconnected from the main component. And this is due to the parsing error. That is, during the inference time, the generated response does not accurately follow the JSON schema, that it cannot be properly parsed into the tag tokens. And in this case, we simply discard it and exclude it from the constructing graph. But actually, this issue can be mitigated if we have multiple times of retry. Next, let's look into different parts of the graph. First, a graph consisting of benign events. As you can see that both graph from Llama 70 billion model and the Distilled model show similar pattern that benign events, how benign events connected to the malicious event are the same. That is through these two tokens, the /c and ipconfig. Next, let's look into the contextual malicious events. Here's the graph from Llama 70 billion model. And for 3 of the contextual malicious events, the 2 of them, index 1 and 2, are connected to the red event as what we expected to see. And the way they connected is also using the rr.rr and the result.dat. However, there's one event that we expected to have a connection to the component, but it's actually disconnected. It's the one index 3. If we look into the parse token, actually there's a discrepancy between that is the token from node index 3 consists of the file name only, but the token from event 1 has not only the file name, but also the full path. And if we look into the real comment of these 2 events, it is actually a design, and it's what we should expect to have. And in this case, although we didn't tackle this issue, but it can be solved like having an additional layer to detecting the synonyms, or specifically, we can try to identify whether a token is passed or not. And if it is passed, we can further extract the file name as an additional token to help the merge or the graph construction process. Next, let's look into the Distilled model generated graph. And roughly speaking, the 2 graphs looks very alike, event 1 and 2 connected to the malicious event, and event 3 are disconnected as well. So in terms of the connectivity, the Distilled model seems working quite well. But if we look more closer into some details, there is still some defect. For example, let's go back into the benign part of the graph. First, you can see that from Llama 70 billion model, the number of links connecting to /c is like 4 edges only from the button. But for Distilled model, there's much more links connecting to the /c. Also, here, the graph, the blue box representing the identified tokens, and the length of the box actually corresponding to the length of the token. So you can see that for Distilled model, 0.5 billion model, the token length seems a little bit longer than what they are presented in the 70 billion model. So that means there should be something wrong in the generated token. So we dive into more details and look to try to identify whether there's some token that are not properly parsed. Here, let's first look into the large language model, the Llama 70 billion model generated. The 4 lines here, the first line and the 3rd line are the actual command lines, and the 2nd and the 4th line are the tokens that are, there's some typo in the tokens. Here the typo, we identify the typo by identifying whether the token is a proper substring of the input command line. Since in most of the cases, it should be that. As you can see, among all the events, these 2 tokens are only mistakes made by Llama 70 billion model. Here, the color means the red color in the 2nd and 4th token means there's a match from the token to the original command line, and the red color means this character should be deleted from the command, and the yellow color means the character should be inserted back to the token. Now, as for the smaller model, it actually made much more typos in the generated tokens. Like there's some, like in the middle part, there's a lot of red zero, which means the Qn 0.5 billion model generated this token having too much zero than it should have. So if we look into different language model generated results, there's some observation. Like first, for Llama 1 billion model, it seems to have more typos, more tokens that are wrong comparing to a 0.5 billion model. But the way it makes mistakes are quite consistent, like having lowercase t replaced by the uppercase e. And as for the 1.5 billion model, no matter it's a reasoning model or non-reasoning model, both seems to work quite well, having little typos comparing to the smaller one. So for quality matters, we recommend using a larger model comparing to a smaller one. But if we try to use a larger model, you may wonder if there's some efficiency loss when incurred. So here we did an analysis. Here's the result. The environment we use VLM to serve language model, and the settings on the top of the slide. Here, for the 4 distilled model, the actual throughput are similar, around 140 to 160 requests per second. And the memory usage are the minimal one that we've tried to launch the language model. And actually, smaller model have much more severe memory bound issues. That if we increase the memory usage from the minimal requirement to full available, like around 80 gigabytes, the throughput actually doesn't increase at all. And also, if we use a less powerful GPU, like 4090, the throughput has a slight drop comparing to H100, but still can attain around 90% of the throughput. As for the large language model, here we test the Llama 30 billion one. The throughput with the minimal GPU requirement can attain around 13 requests per second, and we increase the GPU utilization to 80 gigabytes. The throughput can increase to 16. But there's still, comparing to a smaller model, large model consumes 10 times more GPU memory, but can only attain 1/10 throughput. Now I'll hand over to George for the conclusion.
Okay, great. Okay, so time is almost running out, so I'll give you a very brief takeaways. So thank you, Laura and Jerry, for their amazing presentation. So the first takeaway that we are giving you is that we hope you, from this talk, you can understand why it's important to have a more sophisticated language model that can help you to construct the command line into the graph so that it can have more context awareness during the forensics. And the second thing is that Jerry already showed you a very comprehensive performance comparison between the very small model like 0.5 billion to 70 billion models. And you can see we got a lot of performance gain, but with very minimum quality loss in the real world scenario. So I hope they can persuade you to give it a try. And then the last thing is, and also the best thing is that you don't have to trust us because today we were going to release all the models on the Hugging Face. So right now you can just go to these Hugging Face links, and then you can download the models, and we also provide some example code for you to run the inference. So don't trust us. You can give it a try by yourself. So that's pretty much our talk today, and we are looking forward to have some really good advice and also the feedback from you guys. So thank you again, Xing Kang. Thank you.